Good afternoon. My name is Leonardo Montecchi from the University of Campinas in Brazil, and I'm going to present a paper which is titled An Eclipse-Based Editor for Some Templates. This is a tool paper, and it is a joint work with Federico Moncini and Paolo Lollini from CINI and the University of Florence in Italy, and with Ken Keefe from the University of Illinois at Urbana-Champaign in the United States. In this paper, we present an editor for what we have called Stochastic Activ-ity Network templates. This editor is based on Eclipse, and it is part of a more extensive project that is under development, which is called the TMDL framework. In this presentation, I will first discuss the context and motivation of this work. Then I will present the architecture of the tool, then show an overview of the editor with some screenshots, and then discuss the ongoing and future work that we are undertaking in this direction. So let's first discuss about the context and motivation of this work. In this work, we are talking about model-based evaluation. So we are focusing on model-based evaluation. Model-based evaluation is a well-established technique for estimating non-functional metrics on systems, for example, reliability or performance metrics or performability metrics. And in particular, we focus on methods which are based on stochastic activity networks and stochastic Petri nets in general. So in these methods, you typically have some systems, some system descriptions, some architecture, and some requirements, and some metrics that you need to estimate. For example, it could be mean time to failure, could be throughput, could be some probability of occurrence of some event. So typically an expert in dependability modeling creates the models, which could be, for example, stochastic activity networks. And then these models are evaluated either by simulation or by mathematical methods, and some estimation of the metrics are obtained. One problem in this kind of techniques is that constructing and maintaining models for large systems, large scale evolving systems, like most of today's critical infrastructures, is a very challenging task. This because models need to be changed frequently because the system changes, because you have many subcomponents, many system elements that may have a similar behavior but not identical behavior, so you need to take into account for this and make a lot of similar models but with some little differences, and then you have complex interactions between the components. So if you take, for example, a context in which you have vehicular networks, but other kinds of systems, this is a very big problem in maintaining and creating and maintaining these models. In a recent work of ours, we have introduced the TMDL framework, which is an approach to simplify the construction of these large models, and it is based on the TemplateModels Description Language. That, for this reason, it is called TMDL. So this is an overview of the framework. The framework has been published in this paper in the Transaction Reliability in this year, 2020. Basically, we propose, in that paper, we proposed a workflow for to simplify the construction of these models, and which involved the concept of templates. So in this workflow, it is centered around the concept of model templates. Basically, there are three main steps. In the first step, we have step one, we have an expert in performability modeling that creates a library of reusable model templates, which are models that have some parameters and that can be reused and instantiated multiple times to create some variants. In the second step, variants of these templates are selected from the library to compose a scenario of interest, so to compose a model for a given scenario. And then in the third step, the instances of templates are automatically created and composed by a composition algorithm. So in that paper, we also defined this composition algorithm, which is general, and it is always the same for any kind of model. To apply this approach, so this approach has been defined as a generic approach for different kind of models that are composed by state sharing. To apply this approach, we defined three assumptions, so three requirements for applying this approach. So the existence of an instance level formalism, which is the one which is generated in step 3, so the one which is typically actually used to perform the analysis, which is typically a formalism which is used now, for example, Stochastic Activ-ity Networks. Then the existence of a template level formalism, which is used for libraries, so a template version of the formalism to define libraries, and a concretized function which instantiates instance level models from templates. So if we have these three elements, then we can apply this approach. So the editor that we propose in this paper is a step forward for applying this approach with Stochastic Activ-ity Networks. So in fact, this editor is part of our project for applying the TMDL framework with Stochastic Activ-ity Network, or SAN. And so we need to make sure that these three assumptions are satisfied. For instance level formalism, okay, we have Stochastic Activ-ity Networks, which have been defined in, for example, in this paper from Sanders and Meyer in 2000. Then we need a template level formalism and the concretized function. These two elements have been defined in another work of ours, in a technical report. So in the technical report, which has been uploaded on arXiv as a preprint, formal definition of Stochastic Activ-ity Network templates. We defined the template version of Stochastic Activ-ity Networks, SAN templates or SAN-T, and the associated concretized function that generates ordinary SANs. So just to give a brief overview of what are Stochastic Activ-ity Network templates in our definition, essentially they are a version of Stochastic Activ-ity Networks in which some parts can be left unspecified, including structural aspects. And the main differences with ordinary SAN is that places have a multiplicity, meaning that they can be expanded to multiple concrete places, and that the number of cases of an activity may depend on parameters. So this is a structural variability, let's say. And that also input gates and output gates, connections between gates and places, etc., can also depend on parameters. Then you can check the technical report for more details. So in this paper, we provide a graphical editor for these formalism, SAN templates, to basically practically enable the application of the approach, because to actually enable the application of the approach, some practical tool support is needed, of course. So with this editor, we aim to create a tool to enable modelers to actually define template libraries, and so at least enable the first step of the approach, which is basically create this yellow box here, template implementation and implementation of templates, which will be stored in the library. So let's now see more closely the architecture of our tool. The editor is part of the template modeling environment, or TAME, which is basically the implementation of the TMDL framework discussed before. And it is based on the Eclipse modeling framework, which is a very popular tool for creating models and modeling environment. And it is therefore organized as a set of Eclipse plugins. The tool is organized in a formalism independent layer, which basically contains the core of the tool, which is the TMDL metamodel and the composition algorithms that have been defined in the paper at the transactional reliability. And then we have a formalism specific layer in which we provide the implementation of the template level formalism and the concretized function for specific instance level formalism. So just to better visualize the architecture, here we have a simplified image of the architecture in which arrows mean dependencies. So we have a basic layer in which we have the Eclipse plugins, in particular EMF, but also Series, which is used for the graphical editor, ATL for the concretized and implementation of concretized, and ACLEO for model-to-text transformations. Then we have the formalism independent layer, which is basically the core part of the framework, with the TMDL metamodel and the composition algorithm, as mentioned before. And then the formalism specific, which contains the metamodels for stochastic activity networks and stochastic activity networks templates, and the graphical editor, which are what actually are presented in this paper. And then we have an implementation of concretize for generating SUN from SUN templates, and a model-to-text transformation for generating an input for the Mobius tool, because we need actually to at some point execute these models. So for the editor, for the architecture of the editor, we so basically this yellow part highlighted here. We use Eclipse Series. Series is a tool which is used to define graphical editors on top of the core metamodels, and it uses a declarative specification approach. So it takes care of many aspects of the implementation, and the user just needs to declare how the editor should look like. So basically, we developed a SUN metamodel because many concepts of SUN templates are actually reused from SUN. So we thought that it would be interesting to have a separated SUN model and then a SUN template metamodel that reuses some of the concepts of the metamodel for plain stochastic activity networks, and then a series specification for the editor. In this way, we actually also get for free the possibility to edit basic ordinary SUN models, because as I mentioned, the SUN-T metamodel is basically an extension of the stochastic activity networks metamodel. So just to give an overview of the metamodel, here we have an overview of the core package. So we have a SUN-T meta class. Then SUN-T can have places or place templates. It can have parameters. Parameters can be a simple parameter or an array of parameters. It can have arc templates. It can have activity templates, and so on. So basically, for each element of the SUN-T definition, we have created a meta class in the meta model. Just to give some more insights, then we have the places package. So a place template can have a multiplicity. A multiplicity can be defined as a value, can be defined as an array, as a parametric, so it has a reference to a parameter of the template. It can be defined as a range, so with a minimum and maximum value and a step, and this would define how the place would be expanded in the concrete model. In summary, the Sun meta model is composed of 4 packages: core, types, expressions, and distributions, and 57 meta classes. And the Sun meta model is also composed of 4 packages: core, places, cases, and gates, and 22 meta classes in addition to those reused from Sun. So actually it seems smaller, but actually it adds 22 meta classes. So based on these meta models, we have defined the specification for Sirius. So for example, here we have a timed activity, which has a bordered element, which is a case, which is represented as a blue dot. And so you can specify how your model elements should look like. Here we have a specification of the target of an input gate. So the target of an input gate is a relation, is an arc. The source is an input gate, and the target can be a timed activity or an instantaneous activity, and so on. So this is actually a very interesting way to define our editor, which is provided by Sirius. Okay, so let's now have an overview of how this editor looks like. In this editor is basically what you would normally expect on a graphical editor based on Eclipse. So you have places that have different appearance. So it has some information on the kind of tokens that they can hold. Have a different color if they are extended places, like in mobs. You can see the marking, initial marking, and then you have a property page in which you can assign a name, assign an initial marking, and so on, for example. And you have these properties for all the elements of the model. For example, here we have the property page for cases of an activity template. So an activity template may have a number of cases which is variable, which is given by a parameter or by some expression. So here the property page allows the modeler to say that it depends on a parameter P in this case. And as you can see here, but maybe you can see better in the next slide, you have a palette in which you can use to create the elements in the editor. For example, normal place template, timed activity, instantaneous activity, and so on. This is an example of a stochastic activity network templates. It looks similar to a stochastic activity network, of course, but this green rec element is actually a place template, which is governed, which is parameterized with the parameter S, and this is also an activity template. So connections in the model, connections to template elements are highlighted in green like this, and this is useful for the modeler to have a rapid idea, have an overview of which elements of the model are templates and which other are normal. And for example, these are normal places, and so they are not highlighted. Just to get an idea of how this works, basically from this template, based on the parameters that are assigned in the second phase of the approach. So in the selection of variants, basically different actually concrete sun models can be generated. In this case, we have a similar structure, but here you have two places and consequently two cases of the activity, and while here you have three cases and three activities, three cases of the activity, but the rest of the model is the same. In this case, this was a model that represented the request of different services from an user. Our tool, the complete tool, is published in a public GitHub repository. So this is the address. And the tool can also be installed by adding an update site to Eclipse. So by adding this update site to the latest version of Eclipse, all the dependencies should be automatically installed and also the tool installed. So if you want to, feel free to try it. And now discussing some future and ongoing work on this topic. So which are the next steps for this work? First, of course, completing the implementation of TAME, of the TMDL framework for Stochastic Activ-ity Networks. So, which basically means implementing these colored boxes here, in particular the transformation from Stochastic Activ-ity Network templates to normal Stochastic Activ-ity Networks, which is the concretized function, which will be implemented as a model-to-model transformation, and then generation of input for the models tool to actually analyze the generated models. And this is an ongoing work. We have a researcher, a student working on this. And it is implemented as a model-to-text transformation from the sun meta model to the XML, which is used as input by models. And then we would like, of course, to have an application of this framework for the analysis of real systems to actually see the effectiveness of the approach. So to conclude, in this paper we presented the graphical editor for sun templates, which is based on the Eclipse modeling framework and series, and also based on our definition of sun templates. This is part of the TAME tool, and which provides an implementation of our recently published work. And this implementation is ongoing and evolving, and it is publicly available on GitHub. So please feel free to try it, and of course, contributions are welcome. So please send us an email and get in contact, and we can discuss. Thank you for your attention.